In this lecture, we will see what is a off-nominal tap ratio transformer, and we will try to derive the bus admittance matrix or the Y matrix for such kind of a transformer. Now, we have seen in our previous lectures in the beginning that whenever we are using a per unit system, and let us say that this is a transformer. Here let us say voltage base is V1 and here voltage base is V2. Now if the transformation ratio is same as the ratio of the voltage bases, I will take as base so that we do not get confused. And here it is V1 and V2 to show the transformation ratio. Now whenever this equation is holding, then we do not find any difficulty in using per unit system wherever transformer is present, because whenever the transformation is in the same ratio as that of the base voltages, then the transformer is just reduced to an impedance equal to its leakage impedance. Okay, and we do not have to worry about the voltage basis. I can take only per unit system directly. However, whenever this equation is not true, that is, the transformation ratio is not equal to the ratio of the voltage basis on the two sides, then this transformer model in the per unit system might not hold. So what we need to do, we need to modify this model so that we can show that there is some kind of difference between the various voltages on the both sides of the transformer, because the transformation is not being in the same ratio as that of the base voltage on the both sides. Okay, so let us say that we have a transformer with leakage impedance something, let us say Z. This is a transformer with leakage impedance Z, and its transformation ratio is having a little difference, let us say 1:A, where let us say A is just 1.01. So what does it mean? It means that it is having 1% difference between the various base voltages on the both sides. That is, if this is some kind of magnitude regulating transformer, what it is doing, it is giving a 1% uplift to the voltage magnitude on this side. Okay, so in this case this simple model for a transformer in per unit system is not valid, because the voltage here it is something else and here it is something else. Okay, and we have to see how can we simplify this kind of transformer so that we can use our various mathematical equations which we have derived earlier. So now let's try to derive the equivalent model of such kind of transformer. You see, let us say this transformer is having V1, V2, which is in the ratio as V2 over V1 is equal to A over 1. Okay, and however, the voltage base is V1 base and V2 base. Now I can write A by 1 simply as A by 1 into 1 by 1. What does it mean? It means that I will try to show this transformer as a mixture of two transformers, in which one transformer is having voltage transformation ratio in the same ratio as that of the various base voltages. That is, one transformer having V1, V2 same as V1 base, V2 base, with the leakage impedance, let us say, equal to the given transformer's leakage impedance G, and the second transformer with 1:A ratio with V1, V2 as simply given by this equation. So here what I have done, I have bifurcated this transformer in two transformers where the voltage ratios are like that the first transformer is having the same transformation ratio as the voltage basis on the both sides, and the second transformer is having the voltage ratios just given by this A or this equation. Now what I have done here, I have given all the known idealities of this transformer to this transformer, and this transformer has been made ideal. Okay, so the beauty of this bifurcation is that this thing, the ideal transformer, the transformer, this is ideal and this is non-ideal transformer, which is having transformation ratio in terms of the base voltage only. This transformer can easily be converted into per unit domain just by showing the non-ideality. That is, this transformer is replaced by just an impedance Z, okay, and the other transformer wherein the voltage levels are changing. Up to here, this is voltage V1, and here the voltage has changed to A V1. Okay. So what I have tried to do here is that I have tried to show this off-nominal tap ratio transformer by giving its all non-idealities to a transformer which can be easily shown just by an impedance in per unit form, and the other transformer which is ideal and which is just changing the voltage and current levels and nothing else or non-ideality is present in it. Now we have got some kind of very simplified equivalent model of this transformer. Now we will try to determine its Y admittance matrix or the admittance matrix in the next slide. Now let us derive the Y matrix of a off-nominal tap ratio transformer. In the previous slide, I have shown that an off-nominal tap ratio transformer can be shown as a transformer which is having different voltages at its two ends. Let us say this is the secondary voltage V2, this is current I2, and here this is the non-ideality or the leakage impedance. I have shown this by as admittance in admittance form as Y. Now this off-nominal ratio is just 1:A. Like in mathematical form, if I want to say that, let us say I am having a system in which a transformer is present. It is, let us say, 400 kV base on this side and 200 kV base is on this side. Okay, these are the base voltages. Now this transformer is such that what it is doing, it is changing 400 to let us say 199.5 kV. Now this transformer is having a ratio which is different than the base voltages. So what can I do? I can show this transformer as a combination of two transformers. Okay, this transformer is a transformer which is having the non-ideality or the leakage impedance. However, its transformation ratio is in the same ratio as that of the base voltages. So this transformer can just be shown by an equivalent leakage impedance, and this transformer can be shown by this ratio 200:199.5. That is just that part by which this transformer ratio is off or deviated from the base form. Okay, so what I have done here is that I have changed this kind of transformer into a transformer which is having 400:200 and 200:199.5, and all the non-ideality has been shifted to this transformer. So this transformer has just been changed to this impedance, and this transformer is having this voltage ratio. So I hope now you have understood that what was I trying to show in the previous slide. Now here this was voltage V2, so what will be the voltage here? V2 over A, and here this is voltage V1. Okay, now from this equivalent circuit diagram, what I will try to do, I will try to form the equations such that I can get Y matrix or the admittance matrix. Now that we will see in the next slide. Now let's derive the Y matrix of this given power system in which we have an off-nominal tap ratio transformer. Now I am going to assume the general case where this A is a complex quantity, that is both the magnitude as well as the phases are being changed by this transformer. Now we know that for the Y matrix, what I have all the currents entering into the node. So I should take minus of I2 to get the Y matrix. This will be Y and this will be V1, V2. Now I have to get equations in this form. Now we should also remember that all these quantities are in per unit. You know why? Because here I have taken all the non-idealities in a transformer which was having the transformation in the ratio as that of the voltage basis. Okay, so all these quantities are in per unit. Now I can write from this given network that I1 is equal to V1 minus V2 over A into Y, or I1 is equal to Y V1 minus Y over A V2. Let us say this is equation 1. Now if I divide this equation 1 throughout by A conjugate, I1 over A conjugate, what I will get? I will get V1 over A conjugate into Y minus Y over A into A conjugate V2. So what I will be writing it is I2. But what I need to get? I need to get minus I2 to get the Y matrix. So minus I2 will be minus y over a conjugate into v1 plus y over a magnitude squared. Why? Because a into a conjugate is simply a magnitude squared into v2. Let us say this is equation 2. Now from equation 1 and equation 2 I can write the y matrix. Let us say equation this is 3. So I can write equation 1 and 2 in the form of equation 3, and I will write it as simply I1 minus I2 is equal to y minus y over a minus y over a conjugate y over a magnitude squared v1 v2. So in this way this matrix shows that this is the admittance matrix. However, if a is a complex quantity, then this element, let us say this is element y11, this is element y12, this is element y21, this is element y22. Now you see, if a is a complex quantity, then y12 is not equal to y21. So this is not a bilateral network. Okay. However, if a is a real quantity, then y12 is equal to y21 and it will be a bilateral network. And since this is a real quantity, I can represent it as in the form of equivalent network. Now, taking a case where a is a real quantity, I will try to show this whole network in terms of equivalent network by using various network elements in the form of impedance or admittance. Now let us see how to represent this of nominal tap ratio transformer using normal elements which are having normal impedance and admittance in the next slide. Now from this derived Y matrix, I can make an equivalent network. Now this element, let us say this is bus 1, this is bus 2, this is voltage V1, this is voltage V2, and this is the reference bus. Okay. Now the element connected between two buses is equal to minus of y12. Okay. What it will be? It will be simply y over a. Now this element, what it is? It is equal to y11 plus y12. Why? Because when we will try to derive the matrix Y matrix from the equivalent network, what I will get y11 plus y12 minus y12 equals to y11 equals to all the admittances connected to bus 1. Okay. So in this way, these two elements will satisfy my equation to get the element y11. So it will be simply y minus y over a. Similarly, this element will be y22 plus y12 because it is a real quantity. So only in this case I can represent it using equivalent elements. So it will be simply y over a square minus y over a. Okay. So in this way, what I have done here, I have represented the off-nominal tap ratio transformer with a known identity showing the leakage admittance y in terms of equivalent network where there is no mutual coupling part or the transformation ratio part, and this has been taken care of in the equivalent network elements. So this is just simply, let us say, y over a and this is simply 1 minus 1 by a y, and this is simply 1 by a y by a is common, 1 by a minus 1. So in this way I have derived the equivalent network of the power system in which there was an off-nominal tap ratio transformer. Now if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel. Thank you.